Okay, this is a quick recap of the problems that we did in our Zoom session on April 21st on the concentrations of solutions. So in our first problem, we were being asked to identify the solute. So the solute would be what we're dissolving. That would be our sucrose, would be the solute. The solvent would be the water. And we're being asked to identify whether the solute is ionic or molecular. It is made of all nonmetals, so that would make it molecular. Our first problem asks for the percent of each component. A reminder, that just means the percent of your solute and then the percent of the solvent. So if we want to find the percent of our sucrose, we're simply going to take the mass of the sucrose out of the total mass of solution. So we're using this formula here. And that's in grams, so that'd be 15 grams over 15 plus 50. We want the total mass times 100. And that would give us 23.1% when we put that through the calculator. They want the percent water, which would be the solvent. Okay, I could put the 50 up here in the numerator and then the 65 in the denominator, but a whole lot faster to recognize the solution is only made of the solute and the solvent. So if it's 23.1% solute, I subtract that from 100 and I'd get 76.9% water. So our next question, we have the very same information, but we're being asked to describe this concentration in a different unit, the molality. And molality, as we see here, is moles of solute over kilograms of solvent. So we're separating the two components of the solution. So for this example, we want moles of the sucrose per kilogram of the water. So moles of the sucrose, we're going to calculate our molar mass, shown up here, and that gives us 342.30 grams per mole. And our denominator, we want kilograms of water. The info was given in grams. We need to divide by 1,000, so that would be 0.050 kilograms, which we will put in the denominator here. And we put that through the calculator, and we are going to get a molality of 0.876 molal for the sugar. Again, the very same solution, and we could give this concentration in yet another unit, molarity, which as we see down here would be the moles of solute per liter of solution. So from the previous problem, we can see that the moles of the solute we already calculated. We have all that information. We found our molar mass already. So we still have 15 grams. Our molar mass of the sucrose is still 342.30 grams per mole. But we have some extra work here to do to find the liters of solution. All that we know is the mass of the solution. So I know my total mass of the solution would be the sum of the solute and the solvent. So I have the 15 grams of sucrose, the 50 of water. So I have 65 grams of solution. But I need a volume in liters. So there is a piece of information you would have to ask for, and I gave you a big hint providing it in the problem. Density connects mass and volume. So I'm just going to set up a little ratio here. We are told that we have 1.10 grams per 1 milliliter, and that is for the solution. That's why we had to find the mass of the whole solution. So if I have 65 grams, how many milliliters would that occupy? Some simple cross multiplication, and we see that X would equal 59.1 milliliters. So that means this 65 grams occupies a volume of 59.1 milliliters. But a reminder, our volume for molarity must be in liters. So I'm going to move my decimal 3 places to the left as I divide by 1,000 to go from milliliters to liters. So this would be 0.0591 liters. I'm now going to plug everything in my calculator, do my math, and I get 0.741 molar sucrose. So we had the very same solution, 15 grams of sucrose and 50 grams of water. We found we could describe that to someone by saying it's 23.1% sucrose. It is 0.876 molal sucrose or 0.741 molar sucrose. They're all describing the very same thing, 15 grams of sucrose in 50 grams of water. So we're going to find that molarity is useful to answer other things. Most often we are already starting with a solution, not being asked to always just find the concentration. So in this problem here, we actually have a solution that's available in a stockroom. But I need 100 grams of sodium chloride to be available for some particular reason. How much of that stock solution must I pour into a beaker in order to make sure that if I let that water evaporate, I would have 100 grams of sodium chloride? Okay, so the best thing to do when you see this type of problem where they're asking you something else about the molarity is to remember that this is just a shorthand, what they're writing. What that really means when I see that label is that I have 0.75 moles of sodium chloride for every 1 liter of solution that we have. So now, what are we being asked to find? I need to know, well, how much of that do I have to pour out so that I have 100 grams of sodium chloride? So the clue here is to recognize, okay, I'm looking to figure out what volume I need, but I need it for 100 grams. And a reminder that molarity is in terms of moles, so I'm going to have to figure out how many moles I actually need if I had 100 grams of sodium chloride. So sodium chloride, if we calculate our molar mass, we're going to find that we get 58.44 grams per mole of sodium chloride. So that would be 1.711 moles of sodium chloride. Now I am able to use that information and say, okay, I want 1.711 moles of sodium chloride. And if I just view my molarity as a ratio, 0.75 is to 1 liter, as 1.71 moles is to how many liters? I solve for X, and I would get 2.3 liters, and that is how much of this solution sitting in the shelf that I would have to pour out. Then if I let the water evaporate, I would have 100 grams of sodium chloride sitting there in my container. Right, another problem. Okay, this time we're being asked what mass of sodium chloride, and again, we are told what we have available looking at the label. So I'm going to remind myself that label means I have 1.50 moles of sodium chloride per 1 liter of solution. I want to know what mass. Okay, we'll be able to figure out moles. If we look at that simply as a ratio, I want to know how many moles of sodium chloride if I have 125 milliliters. Now a reminder, we have to have it in liters. So 125 milliliters would be 0.125 liters. Cross multiply, solve for x, and x would equal 0.188 moles of sodium chloride. Okay, we all know if we have moles, we want to go from moles to mass. Very simple calculation. We're going to use our molar mass, and we know that that is 58.44 grams per 1 mole. If we get at our periodic table and add things up, and we do that math, and I would get 11 grams of sodium chloride. And the last problem that we looked at in class was using mass percent to answer something a little more useful. Okay, so we're being told that our ocean contains 3.5% sodium chloride by mass. And if I had 254 grams of seawater, meaning the ocean water, how much salt would I have? So we need to recognize that this ocean water is our solution, and we're being given percent mass information. The sodium chloride would be the solute. So really all that's needed here is understanding that 3.5% means I would have 3.50 grams of sodium chloride if I had 100 grams of solution, in this case the seawater. That's what 3.5% sodium chloride would mean. So we simply want to look at this percent again as a ratio, and we want to know how much of the salt, so our solute, would we have if I had 254 grams of the solution, which is the seawater. Okay, all that I need to make sure of is that these two units are agreeing. I cross multiply, and I am going to solve for x, and I get x equals 8.89 grams of sodium chloride. All right, so hopefully that helps recap the worksheet that we had gone through as we had a lesson on concentrations of solutions.